In this video, we're going to be looking at pointers, specifically pointers in the C programming language, but we're going to be looking at pointers with the approach that in order to really understand what pointers are, we need to have a simple idea of what's happening behind the scenes. What is a memory doing when our program runs on our machine, and what actually is a pointer? And we'll learn how to create pointers, and we'll learn how to use pointers in the C programming language, and also how we can interact with the operating system using system calls that relate to pointers. But first, we're going to look at, in simple terms, what a pointer actually is. So before we dive into creating and using pointers in the C programming language, we should take some time to understand at a basic level what pointers actually are. Since pointers have to do with memory management and memory allocation, we should really try to understand, even if in overly simplified terms, what happens when our program runs in our machine and tries to interact with the memory that's currently living in our machine. So let's say this table here represents the memory in our machine. We've got two columns here. The first one is our address column. This will consist of a bunch of predefined entries, address spaces, so to speak, which can be something like 0x00, and up here we might have 0xFF, and here we might have 0xFE. Really, the values here are completely irrelevant. What's relevant is that each of them should uniquely represent a row in this memory table. So if we say this is our A column, A for address, then here we might have a D column. The D column is for data, and this is where there will be some arbitrary binary data at all times, which is the actual data that's living inside of our memory. So most of the time, we have no idea what's actually in these binary registries. And we don't even know necessarily how big they are, i.e. how many binary digits are in each one. But we can talk to our operating system and ask it some of those questions. Now, we as programmers might go ahead and say, well, I'm writing a program and I have an integer a. Now, when we declare an integer a like this, we're actually telling our compiler to please go ahead and compile some instructions that tell the operating system when it runs this program, look, this guy has an integer a. At some point, he's going to want to put some values in there. Can you please assign somewhere or allocate somewhere in this memory table where he can store a value for this a integer? And the operating system might say, okay, well, I can give you address 0xFB, for example, and there might be some arbitrary data in there already, but we don't really care about that, and we're going to be overwriting it anyway. But essentially, the operating system has now said, well, the binary representation of the value that might go into A can be found in 0xFB. And the operating system knows this, but we don't really know this at this time. So we might continue our program and say, well, actually, A should have a value of 2. So this is the programmatically assigning 2 to A. It's not actually a mathematical equals sign. So A has a value of 2. So now our operating system goes in and says, okay, well, he said it has a value of 2, so I need to put the binary representation of 2 into this corresponding data registry for this A integer, which I know has this address of 0xFB. So it will go ahead and write the binary representation of 2 in here. So let's say that this registry consists of 32 bits. That will be 32, a bunch of zeros basically, and at the end somewhere a 1 and a 0, which will be a binary 2, right? So this is in some ways simplified because 32-bit might sound like a lot, but it's actually not a lot when it comes to memory. In reality, these registries will be a lot larger than that. They'll be able to store a lot more integers than just A. So really, we are simplifying things here and saying, for now, let's just assume that each of these addresses will correspond to a 32-bit D registry. Now, this is all great. So we've just written this simple code, and all of this magical memory nonsense has happened behind the scenes. We have no idea what's going on. But there are actually times where it might be beneficial for us to know, well, I don't just want to know that I have this local variable called A. I want to know which address are you storing the memory that the value for A is stored in at. So I want to know basically what the A value for this integer A is. Or I may even want to have direct access to the binary data that's stored for A. Let's say I want to manipulate these binary digits, but I don't necessarily want to have to do it through a programming interface like this. Or I might just want to copy them somewhere else for safekeeping, especially because, as we'll talk about later, what we store momentarily on this memory here might be gone before we know it. And this is really where pointers come in. So a pointer at the most basic level is just a reference to one of these addresses in the A column, in our address column. So if we have, let's say we have a pointer P, right? Actually, let's do it like this, a pointer P, and that pointer will be pointing at some address in this A column. And let's say, for argument's sake, that it's conveniently pointing at our 0xFB address, which is our integer's A value representation, right? Now, what this means for us in practice is if we have a pointer that's pointing at this address, as I said in the beginning, if you know this address, you can always find the corresponding data registry. So you can always find the actual binary data that's associated with this address. So the term for that is called dereferencing a pointer. If we dereference P, we can always find this binary data. But there are, as always, a few caveats. So as I mentioned briefly, this registry might be a lot larger than just our integer A. And at this point, we've just said, well, P is a pointer, and it's pointing at this address here. But really, neither the compiler nor the operating system knows how many bytes P is actually representing in the data registry. And that's why pointers typically have a type. So since we, in this case, are pointing at integer A, we might say, well, this is an integer pointer. And the way we would declare that in a language like C is we would say int, and we would say star P. So if we declare this in C, we're saying, well, P is not just a pointer, it's a pointer to an integer, a binary representation of an integer in this memory. So by doing that, we are indirectly telling the compiler, if you go ahead and dereference P, you're actually going to want to look for whatever size an integer is in this particular hardware, which in our case was 32-bit. So if we dereference P, it will go into this A table and say, okay, well, I know it's 0xFB, and it will find this binary portion here, and this might be 128 bytes, but it'd say, well, I only want 4 bytes of those, which is 32-bit, because this is an integer pointer. So it will grab, let's say, the first 32-bit, and it will cut off and say, here are the 32 binary digits that represent the value associated with A, which in our case will be 2. So at this point, you might say, well, this is all good and well, but why do I have to worry about this? I have this perfectly valid syntax of int A and A equals 2. Why do I need to care about these pointers, and all this memory stuff is happening behind the scenes? Why should I be using pointers? Well, we're going to be looking at why later in this video, and particularly in the different types of memory which influence our use of pointers. But before we do that, we should look at what we have so far and what that might look like in the C programming language. Because at this point, I'm basically just using a vague pseudocode here. I've literally drawn an arrow saying this integer pointer points to this address 0xFB, which happens to be the address where the binary representation of the value of A is stored. But really, how would you declare and create and declare a pointer in the C programming language? So to do that, let's bring up our code editor. Now you can use any code editor of choice. I'm currently using Visual Studio Code. So let's create a new file here, and we'll call it pointer.c. That's fine. And let's go ahead and, since we're going to be printing something out, let's go ahead and include the stem.io header. Now our program here should have a main method, which is our ng pointer application, which should return an integer, and let's return 0 if everything goes well. And then if we look at our schematic here on the side, we started by declaring an integer A. We can do the same thing. And if we were to compile this as is, we would expect that the compiler would create these instructions telling the operating system, there's an integer A, you should, in the local memory of this application, you should allocate some space to store A. And in our case here, A would be 32-bit, or it would be 4 bytes, which would be 32-bit, right? 32 ones and zeros. Now, we also said, well, actually A is also equal to 2. We can go ahead and do that. So now we're doing the second part of what I mentioned, where the operating system would have to go in and say, okay, well, now he's saying we need the binary representation of 2 to be stored into this memory address for him to look up later. And finally, now comes the magic of declaring a pointer. So declaring a pointer is really very easy. You need to keep in mind that a pointer is not pointing directly at A. if we look at our schematic over here, we're pointing at the address of A. Now, how do we get the address of A? So let's start by using the declaration that we already have there. So we're saying int star p. So when this is telling our compiler, this is an integer pointer. This is a pointer which will point to an address which we assume will store binary data that represents the value of an integer. But now we need to tell it we want it to have the address of A. And the way we do that is using the ampersand sign. So ampersand in languages like C and C++ will always indicate an address of a given variable. So here we're saying, well, ampersand A is actually not the value of A, it's not even the type of A, it's just the address into this ampersand or A or address column in our memory table. Now, if we were to go ahead and print, let's print the value of A, which should be a digit, but let's also print the value of P, which we're using this percentage. So we'll go ahead and print A, and we'll print P. And then for sanity's sake, let's add a new line at the end. So this is our very complicated program so far. Let's go ahead and compile this using the GCC compiler. So we ran gcc pointer c, and we've now got a program. And if we run that program, a.out, we will see that A prints to the value of 2, and P prints to this value, 0x7ff387598c. Now this is interesting because going back to our little schematic on the side here, these 0x values, you may have wondered, what are they actually about? What is 0x? Well, 0x is a hexadecimal representation, or this number is a hexadecimal representation of some large binary number, which is essentially a unique key to this registry. And we're calling this an address. And what's interesting now, if I run A out again, without having changed the code, you'll see this address is slightly different. This is because our operating system is, every time we run A out, is basically saying, well, he's telling me at runtime to store this integer A in an arbitrary address, so it'll just give us one that's available. It's not going to be the same. And this is quite relevant when we work with pointers, is we can never assume that the address, or we shouldn't assume that the address is always going to be the same for where we store our data. Okay, so now we've implemented our little C program here, which does basically what we talked about in the schematic on the side here. So we've declared this integer A, and we've said A has a value of 2, and then we've declared an integer pointer which points to the address of A. Again, this ampersand being the address of A, which is the address in our A column over here. And then we've dereferenced that pointer, this star P, and saying, follow the pointer, go into this address table, say, what is the corresponding binary? And since we're an integer pointer, give me the 32 bits of binary digits that start this address register, and tell me what the value is. And indeed, when we print out that value in decimal, it comes back as 2, which we saw down here. So let's return to our schematic and talk about why pointers are actually relevant. What is the point of this whole thing? I mean, what we've done so far is completely arbitrary. There's no real reason to use pointers for any of this. So memory is obviously a limited resource. We have on our machine, you might have 4 GB, you might have 8 or 16, but it's a limited resource and it makes things faster, which means there's a lot of demand for it. So as a result, the operating system kind of acts as the gatekeeper for the memory that we have available on our machine. All the applications are constantly wanting to use memory. The operating system also needs a lot of memory, especially if you're on Windows. And there needs to be some kind of system in place where applications have memory when they need it, but otherwise the operating system needs to maintain the memory and say you can only have parts of it if you promise to live up to a couple of rules and also if you really need it. So let's talk briefly about the different sections of memory that are relevant to our program here. So we have this table, and as I alluded to earlier, this table isn't really just one big table of memory that we can do with whatever we want. It's actually divided into a couple of sections, and the sections that are relevant for our little program here, let's start with the most boring one. So we might have a section down here at the bottom, which we can call our IS section. This is our instruction set section, which is really the most boring one, but essentially it's when you load your program, I've been talking about instructions throughout the video. So you have these instructions which basically tell the computer, this is what you need to do to carry out or run my program. And to speed things up, we load those instructions into memory. So when we run them sequentially or in parallel, the operating system knows to go into these instruction set memory addresses and say, what's the next thing I need to do? I've done what you wanted me to do. Let's say I've assigned 2 to A. What's the next thing on the list I need to do? That's the most boring part. Then let's jump to the top here. So all of the memory we've been talking about so far, and this whole top part here, is what we can call the stack. Now the stack, you may have heard of something like Stack Overflow, which is a popular website, but the stack really is a section of memory which is meant to be a kind of scratch pad or temporary memory allocation mechanism for programs that are running and need to store things quickly and efficiently, but also need to store them briefly and temporarily. So in our case here, we're saying int a and a equals 2, and we have this pointer, and all of that is happening on the stack. So as a rule of thumb, anything we write inside our program in the way that we just programmed in our C program will be happening on the stack. Now, the stack is great because, as I said, it's fast. There's not much going on. It's basically a portion of the memory that the operating system has said when we started our program, said, well, I see that you're running this program. You're going to need some memory. Take this chunk of memory, take this portion of the memory available to the machine, and more or less do what you want with it. We more or less have control over the memory in the stack. We can, I mean, there are some limitations, but we can do what we want with it. We can be as silly as we want. We can declare pointers. We can do whatever we want. There's nothing really stopping us from doing silly things on the stack. But there are a couple of caveats. The stack, as I said, is meant for being sort of a scratch pad. So let's say we have an intermediate variable. Instead of saying int a and a equals 2, we might say we have an int x first, and x equals 1. And then we take that 1 and put it into a. So then we might say a equals x. And then x is actually no longer relevant because we basically took the value from x and said, well, it's now a, and we don't care about x anymore. Let's say we don't use it anymore in our program. It goes out of scope, as they say. Now the stack, because it's meant to be kind of a scratch pad and an efficient portion of memory that we can use on the fly, it has all sorts of cleaning going on. So things will be constantly monitored, so to speak, and there'll be tabs will be kept on what you've got on the stack. And if the operating system decides it doesn't look like he needs this anymore, it will actually clear things off the stack and make room for other things. So if you have a variable declared and that variable is not used anywhere else, let's say you have it in a function that goes out of scope and you've declared it on the stack, which almost all variables that you declare in a program like C will be, it will go out of scope and the operating system will go ahead and clear that memory, meaning that you cannot reliably in your program at any time assume that things on the stack are persisted in any way. Even not just persisted in the sense you could shut down your program and start it up again, but persisted in the sense that you might have a function A, which has a couple of variables like A and B and C, and then you call a function B, and by the time you call B, A has gone out of scope, and those functions or those integers A and B and C, which were being kept on the memory, on the stack memory, have already been removed. And so really what we need is a way of persisting memory more reliably and saying, this stack is great, I can use it for intermediate calculations, I can use it to quickly dump things on the stack, unless I go completely crazy and cause a stack overflow, meaning I allocate way too much memory. I can do with it what I want, it's great, I love it, but I need a way to reliably get more memory, and I need a way to say, as long as I'm running this program, this memory needs to be looked after, it needs to be curated. The way we do that is we have something called the heap. The rest of the memory here in our little example is going to be in the heap. So this is our heap. Now think of the heap as a portion of memory which is curated by the operating system. So as a rule of thumb, we can't put anything onto the heap. When we're writing code like this and we're saying int a and so on and so forth, it's all happening on the stack. All of the code in our previous example just now was happening on the stack, meaning that the operating system could clean it at any time. if we need to persist data, let's say we have some data which we know is crucial to our application. We need to always have access to it as long as our application is running. We need to put it onto the heap. Now the heap, in terms of the internals in here, in our simplified example, will work in much the same way. It will have an address here, which could be 0, I don't know, FA, and it will have some binary data. And all the rules about using the data types and so on and so forth are the same, like allocating enough bytes and so on. The difference is we cannot just willy-nilly put stuff onto the heap. The way you put stuff onto the heap is you need to ask the operating system for its permission. Now you might say, how do we do that? So let's say we want to have a pointer which points to some data onto the heap or on the heap. The way we do that is, let's say we want to store an integer on the heap. We're going to create another integer pointer. So int star, let's call this s. And we're going to say S is important. S is really something we want to maintain for the application. So instead of just putting it on a stack, we're going to ask the operating system, can you please make space on the heap for our integer s, because it's important to us. And the way we do that is using a so-called system call or syscall. So we go into the operating system, into the heap, and use a call called malloc. Or a variation of malloc. Now malloc is a system call, it's for memory allocation. So we're basically asking it, can you please allocate some memory for us on the heap? We're asking very nicely, we need some memory on the heap to store our integer s because it's important. And malloc is a function which takes as a parameter some size, which will be the size of the memory you want to store. So in the case of an integer, it would be 4 bytes or 32-bit. Or typically what you'll see is you'll use the size of keyword to make it portable. But essentially we're asking the operating system very nicely, look, can you please allocate this memory size for us to store an integer? And the operating system might say no if it's busy, but most of the time it will say fine, but it won't return any status message or anything. It will return a pointer because we have no idea where on the heap. It might have allocated it down here, right? It might say, well, this address down here is free for you to use, which might be some arbitrary value. And we have no idea. So the heap returns a pointer saying, well, okay, here's your memory allocation for this size, but it's going to come back as a pointer. And you can feed that in. That address will be fed into s. So if s is equal to this alloc call, like so, we're assigning the result of this malloc function. That result will be a pointer. And as we recall from earlier, a pointer is just an address somewhere. So in this case, it's an address to the heap memory that was allocated to us very nicely by our operating system. So this is a place where we simply need to use pointers. There's no other way for us to really do this. We can't just say integer A or integer B, because we need to go and ask the operating system, and the operating system can only deal in addresses and says, well, you may have this integer, but you're not in charge of this memory. I need to tell you this is where it goes. And the way it tells you where it goes is by giving you an address. And as we know, an address is represented here as a pointer because we need to know how many bytes we're talking about. So we have this data type of int pointer s. Now, the story doesn't exactly end there because there are a couple of caveats here. So as I mentioned, the heap is essentially a curated part of the memory, but it's curated in the sense that we have to ask modern operating system, can we please have some space to play with our memory here? And the operating system will say, okay, here's your space. And the operating system will assume that you are in control of this memory now, and you will use it as long as you need it. And when you're done using it, you will tell the operating system, look, I'm done with this memory. You can now go ahead and give it to someone else. And the way the operating system expects us to tell it is by using another system call, which is called free. So once we've done this pointer, we've asked using the malloc call, we've said, can you please give us a pointer to some memory that we need? And when we're done, we use it in our code. Here's our code. We go in and say, please go ahead and free whatever was in this pointer s, right? So we basically say, okay, we've run our code, we've done everything we need to do with this heap memory, go ahead and free it. If we didn't free it, what might have happened is our operating system would have been none the wiser for quite a while, and our program might have quit in the meantime. We might have moved on to other things. We might have executed this program, and that would have been a memory leak. We would have leaked memory onto the heap because we're basically playing on the curated heap and we're not cleaning up after ourselves. So whenever you hear about a memory leak, this is usually what it means. It means you've allocated, using a system call like malloc, you've allocated some memory on the heap. You may have used that memory, you may have done lots of different things, you may have manipulated it and so on. But before you exited your application or before you stopped using it, you didn't free that memory. So let's take a look at in C code what a system call like this and interacting with the operating system like this might look like. Now we have this old program, and now we know a little bit more about memory, and we can reference our little schematic over here. But all of this is happening on the stack, right? There are no system calls here, there are no syscalls, there's no malloc or calloc or any other variation of it. All of this is happening on the stack, which means that as soon as this function main ends, all of this would have potentially been removed, or the memory might have been used somewhere else. And if we then have a pointer which expects there to be some integer, maybe there's not an integer anymore. Maybe because it's gone out of scope and another application has put some random memory in there, and we can get into serious trouble either by reading memory that's just nonsense to us, or if we try to access, maybe this address is no longer available to us, we might try to access memory that we're not allowed to access, and then we'll get a segmentation fault and all sorts of bad things can happen, right? So instead, we've got this code. Let's go ahead and ask the operating system very nicely if we can store an integer on the heap. So let's declare a new pointer. We're going to say pointer s equals, and we're going to say malloc. And malloc is this function, the system call I told you about. So malloc, as we look over here, takes a size parameter, which is the amount of size in bytes which we want. Now, we could just hard code it and say, look, we want 4 bytes, which is 32-bit, but to make our code portable, because on different architectures, the integer standard might not be 4 bytes, it might be 8 bytes, it might be 2 bytes, it really depends on the architecture. So we can use this size of keyword to basically have the compiler substitute the correct size of an integer on this system in. If they compile this code for another machine that's not similar to ours, this should still work. So now this malloc call, as I said, at runtime goes into the operating system and says, please, 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 can I have some memory allocation on the heap? It's not always possible. Now an integer is very small and this is a modern machine, so I'm expecting this to be okay, but there may be times where it simply doesn't work. So what we can do is we can check if s equals null. So by convention, if the malloc fails for whatever reason, and the operating system might say, look, I'm just too busy, I can't give you this memory right now, then s is actually null. And since we're trying to work with pointers here, let's just get out of our program and say, well, then we just return -1, something went wrong, we didn't get the memory we wanted. So now we have this integer memory allocated on the operating system. If we got this far, it means we asked the operating system, it wasn't null, so we have this memory available to us. In theory, we could stop our program now, but then we would not have called the free keyword or the free system call, and we would have caused a memory leak in our program. But before we do that, before we play around with that, let's actually try putting a value onto the heap. So similar to how you can get the value out of a pointer by dereferencing, as we did up here, we said take the value that the pointer's address actually corresponds to in the data column and put it into integer x. We can also use it the other way around and say, let's assign the value of s to be equal to 4, for instance. So here we're basically saying, we're dereferencing s saying, this is now pointing at the data portion of this pointer, which will be on the heap somewhere down here. And this is actually going to be 4 now. So we're declaring memory on the heap, and we're allowed to do that because it's been allocated to us by the operating system. And then let's go ahead and see if that worked. Let's go ahead and print f and say s. Let's say heap s. This is a different ballgame altogether. And then let's dereference s and see if it actually stored our memory, our value. And just for argument's sake, we can show the address again. We can say ampersand of s, or just the value of s. should be a bit more consistent. Let's say the dereference value of S here, and the actual value would be the address again, which might be nonsense to us, but it shows us that it's not going to be the same as P, for instance, since P was on the stack, right? And then let's end this with a new line. So let's save this and try running this and see what happens. Now we're going to get a lot of warnings. A couple of these are very justified. So one is saying malloc is actually defined in the standard lib header, which we should include. Now, my compiler is clever enough to figure it out anyway. As you can see, it actually works. But for argument's sake, let's go ahead and include that header, like so. Now, what's more interesting is our output here. So as you can tell, our heap dereference value came back as 4, saying that we have now stored this value on the heap. And the heap address happens to be this 0x55, which is somewhere in this address column. We don't really care. But what's important is it's not the same as this. This is a completely different address. This is a completely different value. And even if we could have said this value here is equal to the dereference value of P. It wouldn't have created some sort of memory relationship between the two. It would have just said, well, this value, binary representation of this value here, should be equal to the binary representation if you follow this pointer. Now, one last thing we should do is note that I didn't use a free syscall in this little program here. So what I've actually done here is I've created a memory leak. I'm now leaking at least 32 bytes onto the heap because I didn't tell my operating system after I was done with this allocated memory, I didn't say, oh, I'm done with it, my program has exited or is about to exit, you should free it up. And in this case, memory leaking 4 bytes is probably not too bad, but you can imagine if a lot of programs are constantly memory leaking, it's really, really bad because the operating system either sees the memory as being in use, so it cannot assign it anywhere else, or it can no longer say anything about what's in the memory. It loses the quality of being able to curate this memory. So what we should really do is free S, which is a very nice sentiment, but we're basically saying, we're done with this, we've printed it out, we've shown that we can dereference and set the value like this. We should free S. So now we've shown how we can allocate memory on the heap and why we need to use pointers. Essentially, we've shown that when you allocate memory on the heap, you will be given a pointer, it will return a pointer saying, well, this is the pointer to the memory that you've asked for, here is your allocation, go ahead and use it, which is why we essentially have to use pointers, but we haven't really talked about why pointers are good and why we should be using them. So as you may know, a lot of higher level languages have abstracted away from pointers and kind of try to keep programmers in this domain up here saying, you should just worry about defining variables and doing with them what you want, writing your kind of business logic, and the lower level code will take care of pointer and memory management and so on and so forth. And there are certainly a lot of advantages to that. It always comes at a performance cost and it comes at a flexibility cost. But they basically said, well, all of this lower level stuff is not something we should worry about as ordinary programmers. But there are a lot of times where it's not just about dealing directly with ones and zeros or dealing directly with memory. It's also conceptually a great thing to be able to pass references to things without passing copies of them. In sense, let's say we declare a function which doesn't return anything. Let's say it manipulates something. Let's say it manipulates an integer pointer, or it manipulates some binary in the memory which should be an integer. But instead of taking an integer and making a copy of it, we're going to take a pointer. Let's just call it PTR. So we've declared a function here which takes a pointer PTR, which should point to an integer in the memory. And we can do anything we want to that memory now. We have a reference to it. It has to be, since this is a pointer, it's been created somewhere else. We don't have to worry about having to declare new memory or anything like that. We can assume, at least we should be able to assume, that if someone's calling this function, they're passing it a pointer to an already existing portion of the memory. So there'll already be 32 bits of binary that we can play with. And we can, again, go ahead and maybe overwrite it. We might say, whatever was in there, we don't care. Now it's going to be 4. And This is quite interesting because you may think this is now local to this function, but in reality, we can do a little test here. If we call manipulates, which is not a very good name, but there we are, with p, and then go ahead and print this out again, and we can run our program. What we'll see is, here's our output. What we'll see is we went ahead and said int a equals 2, all our pointer stuff, we set our pointer up, and we figured out that the dereference value of p is also 2, and everything's fine. Then we manipulated p, and we think, okay, so you messed around with this pointer, but actually we messed around with the binary that's behind that pointer. We messed around with the entry of that pointer in the D column over here. So our function here took the pointer and said, whatever the pointer is pointing at, this binary, those 4 bytes of binary are now the 4 bytes which represent a decimal value of 4. Then we print out this again, we print our same statement out again, and now it's saying A is actually 4, which is interesting, right? So it's saying, okay, so A, which we declared up here and we thought was safe, we've actually gone ahead and changed the binary behind the scenes by using the pointer. Now, as you may imagine, there are many use cases where this is actually more than just nonsense and is actually useful. And I think we should do another video where I'll walk you through why pointers are so great when working with arrays and working with collections of things, and also while working with structs, which are essentially, you can think of it as memory that's grouped together, and you know something about the memory, which means that you can use pointers to navigate around the memory very efficiently, but also very intuitively. Instead of, say you have a collection of integers, you can just move a pointer along the collection, and you know exactly you'll get a new address every time, which is where the next portion of that integer collection starts. But I think that should be for another video. This was really meant as an introduction to what pointers are, what they are in a simple way, what they are in relation to our memory, and why they are important to memory management. So thank you for watching.